Hello, I welcome you all to this another interesting screencast, and in this particular video we're going to be dealing with the second problem, and it reads a horse on the merry-go-round moves according to the equations. R is equal to 8 feet, theta dot equal to 2 rads per second, and z equal to 1.5 sine theta feet, where t is in second. Determine the maximum and minimum magnitudes of velocity and acceleration of the horse during the motion. This problem is coming from the Engineering Mechanics and Dynamics 14th edition by R.C. Hibbeler. We are dealing with the second problem. We already solved the first problem. So we are on case 2, which is 12-118. Okay, there we go. So in this particular problem, I've been asked to determine the maximum and minimum magnitudes of velocity and acceleration. Right, let's write down what we have. So we have r equal to 8, which is a constant, and therefore r dot is just going to be equal to 0, and so is r double dot. We have theta dot equal to 2 rads per second, and therefore theta double dot also is just going to be equal to 0. We have z equal to 1.5 sine theta, therefore z dot, this is derivative with respect to time. Z dot is just equal to 1.5 theta dot cos theta, and theta double dot using the product rule is 1.5 open bracket theta double dot cos theta, then minus theta dot squared sine theta. Alright, so we have all these equations. What we need to now find are all the components which we are later on going to use to find the magnitudes using Pythagoras theorem. Alright, so let's start with VR. We know that VR is just equal to V dot, and this is just equal to 0. That's 0 feet per second, right? And then we have V theta. V theta is equal to R theta dot, and this is just going to be equal to, these are all constants, that's 8 by 2, and this is just equal to 16 feet per second. These are constants. And then we have Vz, which is equal to z dot, alright, and this is just equal to 1.5 theta dot cos theta. So this equation is the one that we are going to use for determining the maximum and the minimum, right? After it's a determinant, right? Because it's the one that has some variables here, they are not constants. Okay, so we are looking at cos theta. You've seen this cos theta here is the one that is determining the maximum and the minimum. If you are to draw cos theta itself, okay, this is 0. Alright, so it will start from there like so, and then it will go like so, right? Remember, this is 1. Okay, let me redraw it properly here, and this is -1. Okay, alright, so we have let's look at the maximum points. So this is the maximum. I'm just looking at absolute values. These are maximums, okay? These are absolute values, right? Okay, and then these are minimums, okay? All right, because you are looking at the horse here that is going up, okay? The horse is going up and down like that, okay? So it's going up and down. All right, it's going around and it's going up and down, right? So right now we are looking at this is speed with respect to the z-axis. Okay, so we'll have the maximum. So if we are to write down here, we are saying For Vmax, this will happen when theta itself is equal to 0, is equal to 180, is equal to 360, and so on and so forth. And V minimum will take place when theta is equal to 90, is equal to 270, is equal to that's plus 180, plus 180, 450, and so on. Right, we can see a trend here, right? So let's write down representative of all these angles. So we can say theta here is equal to 180 n, where n is equal to 0, okay, 1, 2, 3, and so on. Then here we can say theta is equal to 90 n, right, where n is equal to 1, right, and then is equal to 3, then 5, and so on, right? Odd numbers, right? 90 by 1, of course, is 90 by 2 is 180, 90 by 3 is 217. So 90 by 1, 90, 90 by 3, 217, 90 by 5 is 450. Okay, so there we go. So we'll say Vmax, V, of course, these are VZ maxes, okay? So VZ max, okay, will take place, Vmax will take place at theta equal to 180 n, where n is equal to 0, 1, 2, 3, and so on, okay? And then VZ minimum will take place, it will take place at theta equal to 90 n, where n is equal to 1, 3, 5, in that manner, right? Let me rub this. Okay, so given a general formula, again we are looking at absolute values, okay? So let's calculate. Then we'll say V max we'll get one value there at theta equal to just the first one, which is 0 degrees, okay, 0 degrees, and this is just going to be equal to, so we're using this equation, you plug in 0 there. What do you get? 1.5 by theta dot is 2, so this becomes a 3, as a 3 feet per second. And VZ minimum at theta equal to just the first value there, 90 degrees, and this just gives us cos 90 is 0, so we'll have 0 feet per second. So we have these values. So what we need to do now is to quickly calculate Vmax. We calculate Vmax and V minimum, right? Using Pythagoras. So we'll say Vmax is just going to be equal to something like this. So we'll have VR squared, okay, plus d theta squared plus Vz max, like so. Okay, and therefore Vmax will just be equal to, we plug in those values, that's 3 squared plus 16 squared plus 0, and then square root of that, square root of answer, we have a 16.28, okay, feet per second. Then we do the same for V minimum, okay, using Pythagoras theorem, we have VR plus V theta plus Vz minimum, okay, which is a 0. Therefore, our V mean is just going to be equal to a 16 feet per second. Alright, so we are done with this first part. Let's go to the acceleration. Acceleration. So let's find the value. So we have AR is equal to A double dot minus R theta dot squared. Okay, squared. This is just going to be equal to, we know this part here is 0. Therefore, we just remain with that part there. So this just becomes equal to minus, this is equal to minus, this is minus R, which is 8 by theta dot squared. So that is 2 squared by 8, right? And this we get a minus 32 feet per second square. Okay. And then we have A theta, which is just equal to R theta dot plus 2R theta, dot, theta dot, this part is 0. This part is also 0 because theta double dot is 0 and R dot is 0. Therefore, this is just 0 feet per second square. And then this is again the determinant AZ, which is A double Z. And this is going to be equal to, from this equation, theta double dot is 0, therefore this part is 0. So what we remain with is just a minus 1.5 theta dot squared sine theta. Okay, so we want to find again, this is the one that is going to, that has variables, or the determinant for maximum and minimum. The rest are just all constants. Right, so sine here, let's check on sine, because sine is the one that is going to govern this particular function. Okay, so let's draw the sine function here. We know how sine function works. Okay, all right, there we go. So we have this point here, which is 1. We have another point which is minus. So these points here are the maximum points, and then these points here are the minimum points. These are the maximum points, absolute value, and these are the minimum points. Okay, for acceleration. Okay, and let's write them down. Let's look at AZ max. We will look at the angles. So the angles, we are going to have 90. Okay, then this one 270. Then so there's always a 180 in between, right? Okay, then 450 and so on. So writing this just becomes 90n, where n is equal to 1, 3, comma 5, right? 3 by 90 to 70, 5 by, yeah, so something like that. Then A minimum, AZ minimum, we have theta equal to 0, and then 180, okay, then 360, and so on, right? Yeah, so writing this is just going to be equal to 180 n, where n is equal to 0 comma 0 comma 1 comma 2 comma 3 comma and so on, right? So when n is equal to 0, we have 0, and n is equal to 1, we have 180, n is equal to 2, we have 360, and so on. 180 by 3, that's 540. Sine 540 is 0, right? Great. So let's write down this. So we have Vmax, not Vmax. Again, we are looking at absolute values. We have Z max, which will take place, okay, at theta equal to 90 n, where n is equal to 1, 3, 5, in that manner. Okay, and then we have, let me just rub this. Then we have AZ minimum will take place at theta equal to 180 n, where n is equal to 0, 1, 2, 3, in that manner. All right. So let's calculate these values. Again, we are just going to use just first values. So let's calculate AZ max at theta equal to 90 degrees. This is just going to be equal to, we are using this equation here. See this equation? Alright, right. So plug it in there. You expect minus, that's 1.5 by theta dot squared. Theta dot is 2, so 2 by 2 is 4, 4 by 1.5 is 6, so this becomes a 6 feet per second square. Alright, and then AZ minimum at theta equal to 0 degrees, okay, this just becomes equal to 0 feet per second square. So let's find the maximum values. So say A max, using Pythagoras theorem, like we did in the other case, is equal to AR squared plus A theta squared plus AZ max squared. Therefore, our A max is just going to be equal to, grab your calculators, let's work it out. So we have AR is a 32 squared, the other one is 0, then the other one AZ is a 6 squared, right, and square root of that, we have a 32.56 feet per second square. And then A minimum is equal to AR squared plus A theta squared plus AZ minimum squared. Then A minimum is just going to be equal to, when you plug in all those values, it just becomes a 32 there, like so. 32 feet per second square. I think we are done. We found the maximum and minimum magnitudes of velocity and acceleration during the motion of the horse. So let's outline these solutions. We do have maximum value there for our velocity, and we do have the minimum value there for our velocity. And then for the acceleration, we do have the maximum values there. There we go. Right, there we go. And then the minimum value for our acceleration, there we go. Alright, I think this is really about it, and I hope this video was helpful. And if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and I'll see you in my next screencast.